Welcome to SpaceGen Aviation. Welcome to this video about radar technology in aviation. Radar is a key part of modern air travel, ensuring that flights are safe and efficient. Throughout this video, we will explore the basics of radar, different types of radar systems, and how they are used in aviation. Radio detection and ranging. Radar, which stands for radio detection and ranging, uses radio waves to detect objects. It can measure things like an object's distance, altitude, and speed, making it vital for aviation. History and development. Radar technology was first developed in the early 20th century. Originally used for military purposes, it has since grown into a key tool in both military and civilian aviation, helping to ensure safe flights. Importance in aviation. In aviation, radar systems are essential for providing real-time data. They help with air traffic control, navigation, and avoiding bad weather. This ensures that flights are both safe and efficient. Applications in aviation. Radars are widely used in aviation for several purposes. They help air traffic controllers monitor planes, assist with aircraft navigation, predict the weather, and prevent mid-air collisions. Basic principles of radar operation. Transmission. Radar systems start by transmitting radio waves. These waves travel through the air until they hit an object. Reflection. When the radio waves hit an object, such as an aircraft, they bounce back toward the radar system. This is called reflection. Reception. The radar system receives the reflected radio waves. By analyzing this signal, the system can determine the location, speed, and altitude of the object. Primary radar. Primary radar systems operate by transmitting their own radio waves and then receiving the signals that bounce back. This type of radar provides basic information about targets, such as their range and altitude. It's commonly used for initial tracking of aircraft. Secondary radar. Secondary radar systems rely on transponders that are installed on aircraft. When the radar sends out a signal, the transponder on the aircraft responds by sending back more detailed information. This includes the aircraft's identity and altitude, which enhances situational awareness for air traffic controllers. Mode A, C, and S. There are different modes within secondary radar. Mode A identifies the aircraft. Mode C provides altitude information. Mode S allows for advanced data transmission, which can include the aircraft's position, speed, and type. Other radar types. In addition to primary and secondary radar, there are other types that serve specific purposes in aviation. These include weather radar for monitoring weather conditions, ground-based radar for airport operations, and airborne radar for detecting weather and mapping terrain. Radar frequency bands. Radar operates on different frequency bands, each serving specific purposes in aviation. For example, the L-band, with a frequency range of 1 to 2 GHz, is used for long-range surveillance and weather detection. The S-band, operating between 2 to 4 GHz, is commonly used for air traffic control and weather surveillance. Higher frequency bands like the X-band and Ka-band provide more precise data for navigation and weather detection. Radar range and resolution. The range of a radar system is how far it can detect an object, and it depends on factors like the power of the transmitter and the size of the antenna. Radar range. The radar range refers to the maximum distance at which the radar can detect an object. This range depends on several factors, including the power of the radar's transmitter, the size of the antenna, and the frequency of the radio waves. Radar resolution. Radar resolution is the system's ability to distinguish between two closely spaced objects. High-resolution radars can provide more detailed information about a target. Range resolution. Range resolution refers to how well the radar can differentiate between two targets at different distances. The better the range resolution, the easier it is to separate objects that are close together but at different ranges. Angular resolution. Angular resolution measures the radar's ability to distinguish between two targets that are close to each other in angle, even if they are at the same distance. A radar with good angular resolution can clearly separate targets that are near each other in the same direction. Radar displays and interpretation. Radar displays, such as the Plan Position Indicator or PPI, show target positions in a bird's-eye view of the airspace. Another feature, the Moving Target Indicator or MTI, highlights moving objects while filtering out stationary ones, helping operators focus on the most important information. Radar symbology, including various colors and symbols, helps represent aircraft types, altitudes, and flight paths on these displays. Radar limitations and errors. Radar technology is not without limitations. For instance, radar signals travel in straight lines, meaning they can only detect objects within their line of sight. Weather conditions, such as heavy rain, can cause clutter on radar screens, hiding important information. Additionally, reflections from non-targets like mountains or buildings can create false signals, and radar signals bouncing between surfaces can result in ghost targets. Radar in air traffic control, ATC. Surveillance. Radar is essential for air traffic control as it provides continuous surveillance of aircraft. Controllers use radar to monitor the exact position of planes within a designated airspace, ensuring safe and efficient management of flights. Separation. Radar data is crucial for maintaining proper separation between aircraft. By tracking the speed and direction of multiple planes, controllers can ensure that there is enough space between them to prevent collisions, which is critical for air safety. Safety. Ultimately, radar systems play a vital role in ensuring the safety of air travel. They provide real-time information on aircraft positions and movements, allowing air traffic controllers to make quick and accurate decisions to manage traffic flow and avoid dangerous situations. Doppler radar and moving target detection. Doppler effect. Doppler radar works by using the Doppler effect, where the frequency of the radio waves changes when they reflect off a moving object. This frequency shift helps determine the speed and direction of the object. Stationary versus moving. Doppler radar can differentiate between stationary and moving targets. This capability is crucial for filtering out background noise, like stationary objects, and focusing on moving aircraft or weather patterns. Aviation application. In aviation, Doppler radar is used to detect wind shear, which is a sudden change in wind speed or direction. It's also helpful for monitoring weather conditions, allowing pilots and air traffic controllers to avoid dangerous weather. Weather radars. Weather radars are critical for aviation safety. They help pilots and air traffic controllers avoid dangerous weather conditions like thunderstorms, heavy rain, and turbulence. Two common types are pulse Doppler radar, which measures the speed of weather systems, and phased array radar, which provides high-resolution images of weather patterns. Synthetic aperture radar, SAR, and inverse SAR, ISAR. Synthetic aperture radar, or SAR, is a type of radar used to create high-resolution images. It works by using radar pulses over time, which allows it to capture detailed images of the ground or other targets, even through clouds or in darkness. Inverse synthetic aperture radar, or ISAR, is similar to SAR but is used to image moving targets. Instead of stationary objects, ISAR focuses on things like ships or aircraft in motion, providing clear images of these moving objects. Both SAR and ISAR are essential in aviation for mapping, surveillance, and reconnaissance. They are widely used by both military and civilian sectors to gather detailed information about the environment or moving targets. Airborne radar systems. Airborne radar systems are installed on aircraft to detect and track other planes or potential threats. One key system is airborne early warning, which can detect aircraft and missiles at long distances. Terrain following radar helps aircraft fly low by following the terrain. These systems are integrated with other avionics for better functionality. Radar cross-section, RCS, and stealth technology. Radar cross-section, or RCS, refers to the size of an object as seen by radar. The RCS depends on factors like the shape, materials, and angle of the target. Stealth technology is designed to reduce RCS, making aircraft harder to detect by radar. This is important for military aircraft to avoid detection. Radar cross-section, or RCS, measures how large an object appears on radar. The larger the RCS, the easier for radar to detect and track the object. Factors like the shape, materials, and angle of an object affect its RCS. Factors affecting RCS. An aircraft's shape can greatly reduce its RCS by deflecting radar waves away from the receiver. Materials like radar-absorbing coatings can also help reduce radar visibility. Additionally, the angle at which an object is detected influences how large or small the RCS appears. Stealth technology. Stealth technology focuses on minimizing an aircraft's RCS to make it less detectable by radar. By using special shapes and materials, stealth aircraft can evade radar detection, making it harder for radar systems to track them. This technology is crucial for military applications, where reducing radar visibility is often a top priority. Future trends in radar technology. The future of radar technology is exciting. Digital radars are becoming more advanced, offering increased processing power and flexibility. ESA, or Active Electronically Scanned Array, improves radar accuracy and speed. Additionally, artificial intelligence and machine learning are being integrated into radar systems, enabling more automated and smarter decision-making. Importance of radar. Radar is essential for aviation. It helps maintain safe flight operations by tracking aircraft, guiding navigation, and predicting weather. Without radar, the aviation industry would be unable to function safely and effectively. Future of radar in aviation. As technology advances, radar systems are becoming smarter and more efficient. New developments like digital radars, improved data processing, and AI integration are expected to shape the future of aviation. These improvements will enhance safety, accuracy, and efficiency in flight operations. Radar outlook. The outlook for radar in aviation is bright. With continued advancements, radar systems will only become more reliable, faster, and capable of handling more complex tasks. This will ensure radar continues to play a vital role in the future of aviation. To summarize, radar technology plays a crucial role in aviation safety, navigation, and weather awareness. As aviation evolves, advancements in radar technology will continue to drive innovation. Radar will remain essential for the future of aviation, ensuring safe and efficient air travel for years to come. Thank you for watching, and stay tuned for more insightful aviation content from SpaceGen Aviation.